Okay, here in section 8.2, we really begin the Cal BC curriculum of AP Calculus BC. We saw a few lessons in chapter 6 and 7 concerning only Cal BC, but from pretty much here on out, it's just Cal BC topics that we're going to be looking at. And the first one here is something called integration by parts. Just recall, chapter 8 is going to be mainly concerned with some more advanced integration techniques that we never saw back in chapters 4 and 5. Okay, so as a way to kind of build up to this idea of integration by parts, just kind of quickly remember that whenever we used a U substitution prior to this lesson, that was really just the integral version of the chain rule. And we had to do the U-box and several things, but that was the idea. A U substitution really meant we couldn't integrate the problem that we were given, so we had to get something out of there by calling it U to make it work out. So maybe a good example of that, or maybe a simple version of an integral here, would be that we know the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. Of course, this could have been written as 1 over u du equals ln absolute value of u plus c in case that problem required a u substitution. But as a simple integral, we're just going to say it's 1 over x dx. A problem that we weren't able to address back in chapter 5 was the integral of a natural log function. And we really haven't had that ability, and we're going to try to develop that ability here in this lesson. So let's talk about this process of integration by parts. Really, integration by parts is the integral version of a product rule. Remember, there was no product rule really for integrating when we were multiplying two things, so we would have had to have approached it some other way. But in this particular technique, we're going to be looking at products of things inside integrals. So this formula right here, we're not going to spend the time to develop. It's probably better in this particular case just to apply it and see how it's applied. But this is the formula that we're going to use to apply to problems that require this process called integration by parts. So integration by parts requires two things. It requires two functions. One is a simple function to take a derivative of, and one is a simple function to take an integral of. How we make that determination, we'll kind of see with some examples, but that's the idea. For the u, we choose the factor that's simple to take the derivative of. For the dv part of our problem, we're choosing the factor that's simple to integrate. And something to point out is that the left side of this formula here is your original problem. The right side of this equation is the answer to that integral. So we'll kind of see that again as we go through some examples, but just realize the left side of this formula you're seeing right here is your original problem. And we're again trying to identify one of the parts of your problem to call u because it's easy to differentiate, and we're looking to identify one of the other parts of the integral and call it dv because that would be easy to integrate. And then of course we can apply this formula. So as this little picture maybe is implying here, u has found a friend. Our u box was just usually a u and then a du, and then that was kind of the end of the story. But now that we have this extra dv portion that we're trying to identify, u has kind of found a friend here, and that's v. So our u-box is going to grow in size, and I'm going to just call my u-box now this cast of characters. There's several different things that need to go on in our u-box, so to speak, but I'm not going to really call it that anymore. I'm going to call it this cast of characters because there's several characters, so to speak, that need to be addressed so that we can apply this integration by parts formula right here. So what is this cast of characters going to look like? Well, luckily the first part is simple. We're used to writing down u in our u-box, and then we're used to taking the derivative of it to get some sort of du. But remember what was stated over here to the left. We also need to find a dv right here. we need to also figure out something else in our problem to call dv because it's easy to integrate. So if we write down what the dv is here in our little cast of characters, then we know that that's the thing that's easy to integrate so that we get a v. The reason I call this a cast of characters, I suppose, is these are all the things that we need to help our formula work out. You'll notice over in our formula, we have a u, and we have that u here. We have a v, and we'll have that v here. We need another v, which we already have, and then we need a du, which we already have down here. So that's the good news here, is that with this little cast of characters filled out, once you have it filled out, it's just a matter of taking those things and sending them over to our formula for this integration by parts. So other than maybe just giving this little overview, of course I think the best way to kind of see this in action is to take a look at a few examples so we can approach this integration by parts. Okay, so the first problem we're going to address is the ever elusive how do we integrate the natural log of x dx. So this might not be an obvious integration by parts application because, as you saw in the last slide, we're really looking for two things being multiplied because it's kind of the integral version of our product rule. So we need to kind of realize something first. We need to identify the two factors that we're trying to either take a derivative of simply or to take an integral of simply. And again, it might not be obvious that there's two factors here unless you take a step to kind of rewrite ln x as ln x times 1. Once we do that, now we can kind of see that there's two factors being multiplied here. We have a 1 times an ln x. So what we're going to do is just need to decide which one's easy to take the derivative of and which one's easy to take the integral of. And of course in this case, we don't want to call ln x the thing we're going to take the integral of because that's what the problem is. We're trying to figure out what the integral of ln x is, so I hope in an obvious way ln x is the thing that we're going to try to take the derivative of, and then this 1 dx is the thing we're going to try to integrate. So I'm going to always start off by writing down the formula for integration by parts here, and then the main portion to these problems really lies in this cast of characters. If you can fill out this cast of characters correctly, it's really just a matter of taking these things and plugging them in over here in our formula. So what is the u going to be? Well, u is the thing we're going to take the derivative of. dv is the thing we're going to take the integral of. And then it's just a matter of performing those two calculus operations. To find du, we take a derivative. The derivative of ln x is 1 over x, but don't forget the dx. The integral of 1 dx, and be careful with this because we're mixing up derivative steps with integral steps. The integral of dv, which is 1 dx, is not 0. We're taking an integral of 1 with respect to x, so that would just be equal to x. Once we have this little cast of characters in, it's just literally a matter of taking all this stuff and plugging it into our formula right here. So when we do that, let's see what we get. We're going to end up with the integral of u dv. u dv is this diagonal right here that you see highlighted in red. So the u is ln x, and the dv is 1 dx. Remember, this left side of the formula is your original problem. And of course, it is our original problem from above. So luckily, that all works out nicely. So what's that equal to? Well, that's going to be equal to u times v. u times v, I guess, is this top row of information. So the u is ln x, the v is x. I'm going to just write it a little nicer instead of writing ln x x. That can be a bit confusing, so I'm going to just write it as x ln x. We need to subtract away the integral of v du, which would, I guess, be this diagonal in green if you want to look at it that way. v is x, du is equal to 1 over x dx. So we're going to plug that in. Once we have that set up, it's just a matter of figuring out what this right side is equal to, and then we've answered our question. Again, remember, the left side of this formula is your original problem, so we don't need to do anything over there. Of course, x ln x is just x ln x. When we multiply x times 1 over x, we're just left with the number 1 dx. And the integral of 1 dx is very simple and basic. Don't overthink that. The integral of 1 with respect to x is just x. And then we're not going to hopefully forget to put that plus c at the end. So there you go. The integral of ln x is x times ln x minus x plus c. That is one of the very basic applications of this process called integration by parts. Just as a quick reminder, we can always check our answers by taking the derivative. If we were to take the derivative of our answer here, we should get back to our original problem of ln x. And sure enough, when we apply the product rule to this piece, and of course the derivative of negative x is negative 1, the derivative of a constant plus c is 0, so that just goes away. When we simplify that, we'll get ln x plus 1 minus 1, and the 1's would of course become 0, so it does check out. The integral of ln x checks out because of this process of taking the derivative. Okay, here we have another application of integration by parts, but maybe something to realize before we even jump into this process of seeing if it's an integration by parts is to maybe just consider this like we would have saw back in chapter 5 when we first saw these exponential integrals. Would a u substitution work here? Well, if you think about the possibilities, realistically the only thing we could call u is either the x, which wouldn't really work out since that would just be equal to du equals dx. And if we decided to call e to the xu, well, that's just also e to the x. And there's no other e to the x in this integral. So bottom line is a basic u substitution won't work here. Just to kind of point this out, if we had put a power of 2 here on our exponential function, then this actually would have worked out. We could have called u x squared, and then this problem would have worked out because we've actually seen this problem before in this class. But unfortunately, there is no power of 2 on our exponential function, so there is no basic u substitution that'll work out here. So how do we decide to figure out what the u and the dv are going to be? Well, as it turns out here, it's not a quite obvious answer to the question that you should be asking yourself. Remember, u should be the thing that's easy to take the derivative of, dv should be the thing that's easy to take the integral of. But it turns out in both cases, it's easy. If we called u the e to the x, well, the derivative is e to the x. If we call the dv e to the x, well, the integral of that is still e to the x. So that was definitely easy. And same thing goes for the x. If we call u x, the derivative is just 1. That's nice and easy. If we call dvx, the integral of that is, again, really easy. So when I said back a couple slides ago, and in the last slide, we're trying to pick u and v to be easy in one regard, there's one extra thing you're going to have to consider, especially with problems like this, that are going to help you decide which one should be the u and the dv, and that's this little fact right here. Since the derivative of x is 1, which is less complicated than its integral, that's how we know we're going to let u be x. The key to these problems is, once you kind of have this dilemma, is which one's going to give you a simpler or less complicated result. And of course, when we integrate x, we get 1/2 x squared, which is a higher power, and that's more complicated. But if we let u be x, the derivative is just 1, and that works out a lot easier. So that's the idea. If your replacement for u and dv make your integral more difficult, just try switching them. It's usually one or the other, so if you happen to choose wrong, then you'll know that you just need to switch your u and your dv because you chose wrong, and then hopefully in that new version, things will work out. Okay, so now that we know that we need to pick not only the ones that are easy to integrate and differentiate, but now that we know this little fact right here, we need to also pick the u or the dv, depending on which one gives us a less complicated answer. So now that we know that, we can go ahead and attempt this problem. U is going to be x, dv is going to be the e to the x dx part of the problem. So how do we go from here? Well, just like our good old u boxes from before, we take the derivative of u, which would be du, and then the derivative of x is 1 dx, but we'll just leave out that 1. On the dv side, we need to integrate that, so what we can do is get our v, and of course the integral of e to the x dx is just e to the x. Once we sort out this little cast of characters business, we're ready to go. If you look on the left side of our equation again, this needs to be your original problem. If for some reason you plug in the stuff from your cast of characters and you don't get the original problem, you definitely made some sort of typographical error, or maybe you overlooked something. So we know that u is equal to x, and we know dv is equal to e to the x dx, which of course gives us the original problem we started off with. The next thing we need to do is take u and multiply it by v, which is this top row of information. U is x, v is e to the x, so that's of course just x times e to the x. Next thing we need to do is subtract away the integral of v du, which would be this diagonal here that you see highlighted in green. The v is e to the x, and du is equal to dx, so we're subtracting away the integral of e to the x dx. After that, it's a fairly simple problem. Of course, x e to the x stays x e to the x, and we know that the integral of e to the x is itself. So that's going to be minus e to the x, and then just don't forget, especially with the complexity of these problems, that your antiderivative needs to have that plus c at the end. Okay, yet another example of this application of integration by parts. So again, we need to figure out what's going to be u and what's going to be dv. And again, maybe this one should be a little obvious in a sense, because of course integrating ln x is complicated. We just saw in that first example that that required integration by parts. So then if we chose I guess dv to be ln x, then that would of course mean we're doing an integration by parts with another integration by parts problem, and that would just be way too complicated. So in this particular case, I hope it's a little obvious to see that the ln x is going to be our u, and then the integral of x is very straightforward and easy, so that's going to be our dv. So, like you saw in the first two examples, I always start off by writing out the formula so we can just look at it and then populate it with the things that we need to put in there. Things that we need to put in there are going to come from this cast of characters idea that I introduced from before. So, the u is again going to be the ln x, because that's easy to take the derivative of compared to taking the integral of ln x, and then the dv will be the x dx portion of our problem. We can go ahead and fill in our cast of characters now. The derivative of u is of course 1 over x dx. The integral of dv, which is just x, would be 1/2 x squared, or I'm going to write that as x squared over 2. Once we have all that, we're ready to take all of this information and plug it into the formula. This red diagonal here is the u dv, so we're going to take that and plug it in, and again we should get our original problem on the left side of this equal sign, on the left side of this formula. So we definitely got our original problem, so that definitely worked out. Next we need to do u times v. U times v in this case is going to be x squared over 2 times 2 times ln x, and I'm going to just put that x squared over 2 in the front of it just to make it look a little more easier to read. From that we need to subtract the integral of v du, which is this diagonal that I highlight in green. We're going to have to plug in the x squared over 2, and then the du is 1 over x dx. Once you do that, it's just a matter of taking this new integral in the problem, and if you need to, maybe with the u times v, simplify it a little bit, but there's really not much we can simplify that to be, so I'm going to leave that alone. You'll notice over here in our integral, we have an x in the bottom, and we have two x's in the top. So of course we can cancel one of those out in the top and the bottom, and we're just left with x dx, and then this factor of 1/2 I'm going to pull out to the front. After that, we have a very easy integral on our hands. The integral of x is of course x squared over 2. Don't forget to put the plus c. I suppose we could leave that as the answer, but I'm going to just clean it up just to make it look a little bit nicer. And of course that 1/2 times x squared over 2 just becomes 1/4 x squared. And again, don't forget the all-important plus c. Okay, we have a few more examples here of some integration by parts and some AP test practice. Here we have the integral of x times cosine x dx. Again, I don't want to really neglect this first step you really all should be thinking about, just because you never know what kind of integral is going to be presented to you. And can this integral be done in an easier manner? Can we simplify it? Well, of course no. Can we call something u to make this problem work out nice and easy? Well, our only option would be x. That's not going to help us. The only other option would be cosine x. That's not going to help us. So this is definitely a use of integration by parts, because we have two functions being multiplied by each other, where a simple u substitution will not work. So because of that, we need to use our integration by parts formula. Again, I like to write that down just as a beginning start to these problems, so we can kind of plug in what we need to know. And the stuff we're going to plug in, again, comes from this cast of characters. So if you think back to the idea of which one should be u and dv, realistically here, either one could be u or dv. The derivative of x is easy, the integral of x is easy. The derivative of cosine is easy, the integral of cosine is easy. So then which one do we choose? Well, if you refer back to a couple slides ago, we need to kind of also consider this one extra idea. Which one would become less complicated when you choose it to be either u or dv? And of course, in this case, we would want u to be x because its derivative is just 1. So that would of course mean our dv would be the rest of that problem, which would be the cosine x dx part. So, like I said a second ago, to take the derivative of u, which is x, is nice and simple. Du is equal to dx, and then the integral of cosine x with respect to x, or cosine x dx, is just sine x. Once we have all that populated in our little cast of characters there, it's just a matter of plugging what we know in. This red diagonal here should be the original problem, and it certainly is. It's x cosine x dx, so that checks out. Then we need to take the u times the v, which is this top row at the top of our cast of characters, so that's just going to be x times sine x. And then we need to subtract away the integral of v du. V is sine x, du is just simply dx. And you can see these problems are fairly straightforward after you fill out this cast of characters and plug in everything into the formula. It's very straightforward. Of course, x sine x just stays x sine x, and when we integrate sine x, careful here, that's negative cosine x. But of course, since we're subtracting that negative cosine x, we can just simply put that as positive cosine x, and then again, don't forget the plus c. In this particular problem, an AP test problem, it's presented in a way that if you're not fully familiar with integration by parts, you might look at it and just think, wow, this is a really complicated problem because of all the stuff that they're presenting here to you. So let's see what's going on. They're telling us that the integral of a function times sine is equal to this stuff over here. And then they want us to find what that function would have been so that we get this antiderivative that you see circled right here. So how do we know that this is a problem that's trying to get us to see integration by parts? Well, you can already appreciate from the original problem, we have a function times another function, and there's no way to do some sort of easy u substitution here. The other little kind of key to maybe seeing that this is integration by parts is that we see two terms here being multiplied, and then we have an additional integral here to the right of that. Because of that, we're going to have to use integration by parts to get us to figure out what that original function would have been right here that was multiplied by sine to give us this antiderivative right here. So let's see how we can approach this problem. And of course, we need to start off with this cast of characters. So what's going to be the u and what's going to be the dv? Well, again, go back to this idea of what's simpler to integrate versus differentiate. If we had chosen f of x to be dv, I wouldn't have really known what to take the integral of for f of x. They don't tell us what the antiderivative of f is, so we really wouldn't have had anything to write had we called f of x the dv. But luckily, since we're calling it u, we know the derivative of f of x. So of course that means the dv portion of this problem is going to be the sine x dx. So if we take the derivative of u, we get du, and if we take the derivative of f, that's of course f prime dx. On the integral side of our cast of characters, the integral of sine x is of course negative cosine x. So let's go ahead and apply our formula and see how all of this stuff is going to tie together so that, again, don't forget what we're trying to do. We're trying to find what that original function was that gave us this problem to begin with. So if we start filling in what we have, and I kind of ran out of space here so I could give it enough space, just realize that the left side of our integration by parts formula should give us the original problem, and it certainly does. U is f of x, dv is sine x dx, so it gives us this part that you see in red. So that's just our original problem, so we're going to kind of ignore that for a second. We need to next take u times v. And you'll notice u times v gives us exactly what we see right here in our problem. Negative f of x cosine x matches up perfectly. So we definitely know we're on the right track with this problem. Be careful, we need to subtract away from the formula. I know there's a plus here, but we'll address that in a second. We need to subtract away the integral of v du. v du is going to be negative f prime of x cosine x dx. And now maybe you can see why there's a plus right here in our problem from above. Of course, we can take these two negative signs and just make that an addition. And now you can see we've matched up this problem basically identically. We have a negative f of x cosine x right here. And then we have an addition of some integral that you can see right there as well. And I'm making this a little messy here by circling all of these, but I hope you can see that this definitely was the right path to go on. So what can we identify from this problem? Well, you can notice f prime of x is matching up with 3x squared. And if we know that f prime of x is matching up with 3x squared, then to find f of x, we would just need to integrate 3x squared. If f prime of x is 3x squared and we're looking for f of x, then we just need to take the integral of 3x squared, and that'll of course give us that function f. And of course this is a nice and easy integral. The integral of that is just x cubed. So the function that gave us this whole big result that we saw in this problem to begin with was just the function x cubed. Okay, here we have another typical kind of AP test question where they do what I think makes some of these problems seem overly complicated but actually easier, and they don't give us any functions at all. They just give us the notation for these functions, a table of values, and it's our job to kind of figure out what's going on here. So we're given this table of values here. They give us this little bit of information, but we really don't need it right now since we don't know how it's going to play a part. The main thing we should be focusing on is this, since that's the problem that we're trying to figure out. And you'll notice we're taking two functions and multiplying them times each other, and there is no obvious u substitution that we can use here. And if we're ever multiplying inside of an integral, I hope the one thing you've kind of taken away from this lesson so far is that should be an application of integration by parts. So again, I'm going to start off by writing our formula. So now we're going to have to make a big decision. what's going to be the u, what's going to be the dv, and again, remember, we're looking for the thing that's easy to differentiate versus the thing that's easy to integrate. And here I hope it's really obvious. If we call u f of x, that's of course easy to take the derivative of. If we call dv g prime of x, that's easy to take the integral of. So let's go ahead and proceed with this problem in that manner. If we let u be f of x, then that would mean du is equal to f prime of x dx. If we let the dv be g prime of x dx, then of course the integral of that is nice and easy. That would just be g of x. Once we have that cast of characters filled in, it really is just a matter of taking all of this and plugging it in. So again, the u dv should be the original problem you started off with. If you take that diagonal in red there and plug it in over in our formula, we'll certainly get f times g prime dx, which is the original problem we started off with. I think the one other thing I'm kind of neglecting to not say here is this is a definite integral. It's going from 0 to 1, so we need to make sure that we put those bounds there from 0 to 1. The next thing we need to fill in is the u times v, which would be the top row of our cast of characters. Here that's just going to be f of x times g of x, but remember, we just took an antiderivative, we took an integral, so that would mean we need to put that bar so that we can apply the fundamental theorem of calculus. So it's going to be f of x times g of x, and it's going to need to be evaluated from 0 to 1. I think that's going to be the one thing that might have been easy to overlook had you not seen an example like this. Okay, the next part we need to address is the integral of v du. We need to subtract away this green diagonal in our cast of characters, so when we plug all that in, we'll be subtracting away f prime of x times g of x dx. And again, this is a definite integral, so we need to put those bounds from 0 to 1. Okay, so definitely looks like a mess of sorts, but there's a lot of easy stuff we can do here. The first thing we're going to address is this thing right here so that we can apply the fundamental theorem of calculus to it. If we plug in the top bound and if we plug in the bottom bound, we should be able to do that using, again, the fundamental theorem of calculus. The second thing we'll need to address is this second piece that you see now underlined. And you'll notice the information they gave us from above helps us out immensely. They tell us that the integral from 0 to 1 of f prime times g dx is all equal to 5, which means this entire thing just all disappears and becomes the number 5. So let's go ahead and apply all those processes here. We need to take the top bound of 1 and plug it in, so it'll be f of 1 times g of 1. We need to take the bottom bound of 0 and plug it in, so that'll be f of 0 times g of 0. And again, we need to subtract because of that fundamental theorem of calculus. And like we said a second ago, this whole part underlined in purple here just becomes 5, since that's what they tell us from above. After that, it's just a matter of looking up some values in our table. You can see from above, f of 1 is equal to 4, g of 1 is equal to 3, f of 0 is equal to 2, g of 0 is equal to negative 4. And if you just don't kind of get mixed up in the arithmetic here, we need to do each of these individually. So 4 times 3 is 12, 2 times negative 4 is negative 8, but since we're subtracting that, that would be a positive 8, minus 5. And of course, that final answer, when you evaluate all that, is just choice E, or 15. Okay, last two slides address a bit of good news regarding these integration by parts problems. There is a shortcut which is called the tabular method for doing these problems. I think the only maybe downside is it usually only works in certain forms of these integration by parts problems. So of course the integration by parts is used when we have two functions being multiplied by each other and there is no u substitution we can use. But this tabular method works especially well when one of your functions differentiates eventually to 0 and when your other function integrates repeatedly. Not sure if you can visualize what that would kind of look like, but that would kind of look like these examples you see here. This tabular method works fantastic when you have x to a power times sine of something. That x to a power, of course, when you take its derivative, will eventually become 0, and sine just repeatedly integrates. It goes back and forth between sine and cosine. Same thing in this second one, and same thing in this third one. So when you see problems like this, this tabular method, once you see it, is just a really quick way of maybe doing these problems a lot easier. So let's go over the process of setting up this table to make this integration by parts work. So in this example, we're going to integrate x squared times e to the x dx. The way this works, or the table that we're going to set up, is we're going to set up our first column and title that alternate signs, set up a second column where we have u and then the derivatives of u, and then in the last column we're going to figure out what dv is, and then all of the integrals of that. And then you'll see how you put all this stuff together to get your answer. So always when you're doing this tabular method, you're going to start off by putting a plus sign first. U and dv. Well, again, u needs to be the thing that's going to eventually take derivatives of to become 0. So of course in this case, that's just the x squared. The thing that's going to integrate repeatedly and never become 0, in this case of course, will be to the e to the x part. The way we fill in this tabular method is we just work downward. If this first column says to alternate signs, then that would of course mean the next row would be a negative sign. In the next row under x squared, we're of course going to take the derivative, which is 2x, and then in the next row for dv, we're going to take the integral, which is itself, e to the x becomes e to the x. We repeat that again. The next sign, of course, since we're alternating, will be a positive. The next derivative of 2x will just be a 2. And luckily again, dv is just e to the x, so again we also have another integral that's the same, e to the x. The last step, you could put a negative sign, but I usually won't put that last sign there because your last step is to stop when you get a derivative of 0. It's up to you if you want to put that negative sign there. It'll never really play a part, but I'm not going to put it there because we stop. Because we got down to a 0 derivative. We're going to differentiate until that 0 derivative finally appears. And then of course we also need to fill in our last column here. Again, the integral of e to the x is e to the x. Okay, so this little tabular method isn't too hard to fill in. It's very straightforward and basic. So how do we take this information and determine what our answer is to this problem up here? Well, it's a pretty easy process. What you have to do first is go across. That sign applies to the first row, or in the second column. So it's going to be a positive x squared. After that, we're going to multiply to run to one row below where we're at. So we're going to go across and then down one row, which means we're going to have positive x squared times e to the x as our first piece of the answer. And then we just repeat that till we're out of rows. Again, we're going to go across as the sign and then down to multiply. So it'll be negative 2x times e to the x. Again, we'll go across as the sign and go down one row by multiplying, so that'll be positive 2 times e to the x, or plus 2 e to the x. Since we ran out of rows to work with, that is our final answer. Just again, don't forget the all-important plus c, since that's our antiderivative. And just like that, a fairly easy process to doing this integration by parts when you can use this tabular method. Okay, just one more illustration of this tabular method. Again, same idea from before. We start off with a positive sign. Again, the u and its derivatives needs to be the piece of our problem that will eventually take a derivative down to a 0. And in this case, it's easy to see that's the x squared. The thing that's going to repeatedly integrate, in this case, will be sine 4x. So to go to the next row, we're going to of course alternate signs by putting a negative. The derivative of x squared is 2x, but be careful here. the integral of sine 4x is not negative cosine 4x. You have to be aware that when you take this integral, that would be an application of a u substitution, since that's not a plane x inside of sine. So if we call u 4x, then of course du is equal to 4 dx, but since there is no extra 4 in our problem, we would have to move that over as a 1/4. I guess that's really the only thing you need to realize, so that when you take this integral, it's not just negative cosine 4x, it'll be negative 1/4 cosine 4x. Once you kind of get over that little idea and not forget about your whole u substitution process, because that can appear in these types of problems, really the rest of this tabular method works out quite nicely. The next symbol we'll put as a positive. The derivative of 2x is 2, and be careful here. When we take the integral of negative 1/4 cosine 4x, we really aren't considering this piece yet. The integral of cosine 4x would be another use of our u substitution, which would be 4x, which would then produce another 1/4 in the front of our integral. So since the integral of cosine 4x would be sine 4x, we would also have to multiply by another 1/4, which gives us negative 1/16. Now we're almost done with this problem because we've differentiated all the way down to getting a 0. And then in our last integral, just like you saw above, the integral of sine 4x would be negative cosine 4x. But since we had a negative from above, that would become a positive, and then just like you saw from before, we'd have to have an extra 1/4 in the front of our integral. So 1/16 times 1/4 would give us 1/64. So just be kind of careful with this kind of a problem. That's why I wanted to do this as the last example. So you can kind of see that this 1/4, because of the u substitution, will be present in every one of these steps when we're taking the integrals. Once we have all that, it's just a matter of making this mess turn into our final answer. So again, the way we get our answer is we go across and then multiply down. It's going to be positive x squared times all of this. And if you kind of make it look nice, I'm going to put that negative 1/4 in the front, and then the x squared cosine 4x. Again, we're going to go across and multiply down. It's going to be negative 2x times negative 1/16. And if we simplify that, that'll of course be positive 1/8 times x sine 4x. For the last one, again, we're going to go across and then multiply down. It's going to be positive 2 times 1/64, which can, of course, reduce to be 1/32, and then we have cosine 4x, and then just again, don't forget the all-important plus c.